Thank you, John. I always begin a presentation the exact same way, so if you've heard me speak before, forgive me. But a couple of things I'd like to point out on this title screen. One is that, if you know me through my books, I have Mario Triola. That's my official legal name, Mario Triola. But I like to go by Marty Triola. I'd really like to go by J.K. Rowling. And the second comment about the title screen would be this. I don't have a handout, but if any of you would like a copy, a PDF copy of all of the slides, there's my email address. Just send me a request, and I'd be happy to send back a PDF file of all of these slides. So if you see anything that captures your interest, you don't necessarily have to frantically try to scribble down some notes. GAISE, G-A-I-S-E. How many of you know what that stands for? Well, that's surprising. In the statistics community, it's representative of guidelines for assessment and instruction in statistics education. Today, though, it's greater assessment of innocence with a statistics education. So a new meaning just for today. Case one, and some of you might be familiar with some of these cases, some not. And I do have to disclose that not all of the cases are necessarily involving crime per se. Some of them might involve some other legal aspect. But when I developed this proposal back in, I don't know, February, I had to put something down, and I found that in some cases I could take a slightly different path. But we have Nurse Kristen. She was suspected of killing some of her patients. Now, if we look at the shift data, when she was on duty, 40 people died and 217 survived her. When she was off duty, 34 people died when 1,350 survived. Now, we could just think informally about those two proportions, and we could see that there does appear to be a substantial difference. And in statistics, this would be a good application of a formal method of hypothesis testing. Compare the two proportions. And you could use either one of two methods. You could do a hypothesis test of two proportions, or develop a little contingency table that looks just like what I have on the screen, and treat it that way. Here's a graph. Now, one of my points here is that very often, like when we teach a typical stat course, we might use graphing sort of superficially. We might think about histograms, for example, as a preliminary investigation into whether or not the sample data appear to be from a normally distributed population. But in the real world, graphs really do have a strong impact. And in this particular case, if I were making a presentation to a jury, I would make heavy use of this particular graph. If I'm trying to convince jurors of what a p-value is and the statistical significance of those results, that would be one thing. But to have them look at that graph, that's really powerful. So something to think about, the importance of graphs that would be far beyond what we typically do in our intro stat course. Cover them pretty quickly and then move on. And here we can see that the difference is quite dramatic. If I run those data on a TI-84 plus C, look at that p-value. It's in scientific notation, and it's a decimal point followed by 19 zeros. So with that many zeros, that's clearly beyond a reasonable doubt, so she's guilty. But now we come to interpretations, another really important aspect of our intro stat courses. We don't want to simply look at a result and say reject the null hypothesis, fail to reject the null hypothesis. We really want to think very carefully about what we conclude. So here we would reject the null hypothesis of independence between Gilbert working and deaths that occur. We might say it appears that a higher rate of deaths is associated with Gilbert working, but that's not proof of causality. Now, what happened? George Cobb, a renowned statistician, he said that you could use the data for grand jury indictments, but don't use the data in the trial because of the fact that the data don't show the causes of deaths. And so Gilbert was convicted from other evidence. They did not use that data in the actual trial. They used it for the grand jury indictment, but they weren't allowed to use it in the actual trial. Very important, careful interpretation of the results. And then speaking of George Cobb, back in 1987, he wrote this article, Introductory Test Books, A Framework for Evaluation. One of his points was about real data. This keeps wanting to jump ahead of me for some reason. And he really made the point that real data are important. Are the data sets real or fake? I hope that we've seen the end of hospitals ABC, corporations XYZ, and those sorts of things. This is back in 1987. And not coincidentally, that's one of the 6 guidelines for assessment and instruction in statistics education. Use real data extensively throughout the stat course. Case 2, sobriety checkpoints. My wife, at one point, when we lived in Dutchess County in New York, she was appointed the Stop DWI coordinator. And in that function, she would be given all of the money from Stop DWI fines. And she had a budget of about $1 million a year to spend to fight drunk driving. We're both educators, and she was heavily into the education aspect of it all. So that she did a lot with education, but one of the things that she did was to fund sobriety checkpoints. So that would be kind of fun for me. I would enjoy it. We'd go out to a sobriety checkpoint at midnight and watch the whole process being observed. And they would be very careful in how they did that. To not back up traffic too much, they had a system of systematic sampling. They would stop every 5th driver. And if the 3rd driver came along, singing really loudly with a window rolled down, and they'd be really anxious to stop them, they could not. They had a citizen observer there to verify the fact that this was systematic sampling, that they were not stopping people at random. And right now in New York City is a big controversy, stop and frisk. This would be one way to get rid of the controversy, do some kind of a systematic sampling. One of these sobriety checkpoints, I saw a former student come along and get arrested and taken away in handcuffs. There was a press there at one of them, and they wanted a photo of somebody in handcuffs. So I volunteered. I put my hands behind my back, and they put handcuffs on me, and they took a photograph of me from the back. But I'll tell you, that's a strange feeling to be in handcuffs. So a point here is that there are extensive alternatives to what we typically do in many of our examples and exercises, simple random sampling. In fact, in our typical courses, and in reality, it's very difficult to really get a truly simple random sample. So we make extensive use of alternatives to that. Here's one that's practical for your classroom. Convenience sample. Sample your students in your class. Just ask them to raise their hand. How many of them are left-handed? How many of you are left-handed here? Okay. 2, 4, 6, 8, something like that. Yeah, so based on that, I could count the number of you, count the number of people here, and develop an estimate of the population proportion of people that are left-handed. Now, you are a convenient sample. You conveniently showed up here today, and I thank you for that. But is there anything about you that would make you a biased sample? Is there any reason why anybody would be more likely or less likely to be here because they're left-handed or right-handed? And I would say, no. Even though you're a convenience sample, you would make a good sample, and I would expect that you would be representative of the population. And looking at the number of hands that went up and looking at the size of the group, I think the result would be pretty good. So there's Simpson there with his leftorium. Case 3, election ballots. This is in New Jersey, Essex County, New Jersey. Nicholas Caputo, he was appointed as a county clerk, and one of his functions was to randomly select the order of names on the ballot. Okay? So, and really we're concerned about Democrats and Republicans. So he had 41 ballots. If he did use truly random selection, you'd expect that about half of them, roughly 20 Democrats on the top line and 20 Republicans on the top line. But no, it turned out that among the 41 ballots, 40 cases, the Democrat won the top line. Now, unfortunately for him, nobody observed the actual random selection process. He said that it was random. The Republicans said, no, it was not, that you don't get those kinds of results by randomness. So, we have a probability we want to know about. Sample size is 41. We have a null hypothesis, random selection. Alternative hypothesis that the proportion of Democrats is greater than 0.5. There's the graph of the actual binomial distribution. Now see, right away, we might look at that, we might think, well, let's jump in and let's use the normal distribution as an approximation. But can we do better than that? There's the actual binomial distribution, and we could see that 40 and 41 are way out there. They kind of fall off the scale. So their probabilities are quite small. There's the normal approximation solution, a z-score of 6.09, which would give you a p-value of 0 plus. Okay, and there's the exact solution that I could get by using the actual binomial distribution. Instead of 0 plus, I'm looking at that. So this 0 plus is more accurate than the other 0 plus. But if I were going into court to argue this, I would want to use the, this keeps wanting to jump ahead of me for some reason. Let's see. You can see what happened. Okay, there's the exact binomial probability distribution. This is what I would use in court if I were presenting this in court. I wouldn't want to use an approximation method. I'd want to use the exact method. And here's another point. As we move along in our stat courses with technology, things are changing. 15 years ago, we would all, or many of us would say, well, if the sample size was more than 30, we could go ahead and assume that the population standard deviation is known and use a z distribution, a normal distribution with a z-score. But now with technology, we can use the t distribution, and so we don't have to worry about degrees of freedom like 147. We can get exact values from technology. So technology allowed us to say, let's use the t distribution when we should, instead of that normal distribution, that rule of greater than 30. Okay, so normal, we might think about dropping that and using the exact probability from a binomial distribution. And so what happened, the county clerk lost his job. It wasn't really a criminal offense, but he did lose his job. Okay, if you're using an exact method with the binomial distribution, it's easy if the test is one-sided. It's easy if the test is two-sided and the proportion is 0.5, which often happens. Now, if it's two-sided and the probability is not 0.5, it starts to get a little tricky. So if it's two-tailed, there's no clear definition of how to go about that. One approach is to let your p-value be twice the minimum of the left tail and the right tail. That's one approach that's commonly used. But this whole exact method is criticized somewhat for being too conservative. How? Too conservative in the sense that the probability of a type 1 error is bounded above by alpha. Okay? So your actual probability of a type 1 error is always alpha or below, and sometimes it might be way below. So there might be a case for using other approximation methods that give you better results than the exact method. Two proportions with the exact method, the calculations really get messy, but you could use Fisher's exact test and come up with exact probabilities that way. Again, taking advantage of technology. And here I worked a little bit to find two proportions that were convenient. 5/20, 5/62. If you use the normal approximation method, the p-value is 0.044. If you use Fisher's exact test, the p-value turns out to be 0.058. So you'll get different conclusions here. Which one would be better? I would go with Fisher's exact test. It's more accurate. And speaking of randomness, this is an activity that I really love. You take your class, have them all flip a coin. Tell those that got heads to go home and flip a coin 200 times and record the results. Tell the other half that got tails to go home and fabricate 200 results, okay, and write them all down. Then you come back next class. You could walk around the class, pick up any piece of paper, and in seconds you could tell if they actually did the real flipping of the coin or if their data were fabricated. Okay? If they actually flip the coin, there's a probability that of 0.97, so that's quite high. You're almost sure that you're going to get a run of 6 heads or 6 tails at least. They make them up. It's been my experience that students almost never pick a run of 6 heads and 6 tails. So what this does, and especially if you do it in the beginning of the course, it demonstrates that you have the ability to distinguish between data that is real and data that is fabricated. So they'll be very reluctant to go out and fabricate anything that's supposed to be real. Here's a typical result, and I just did a random selection of zeros and ones if you want to simulate this, and you can see right there that there's a run of more than 6. Great activity. And activities are things that we should be doing in our STAT courses. If you could personally involve your students, you're going to make your course more lively and more personal, more interesting, and more meaningful to them. Another proportion example, Wittes versus Georgia. Jury pool of 90 people was supposed to be randomly selected from a population with a 27% rate of minorities. Out of the 90, they got 7 minorities. Okay. There's the exact binomial probability, bunch of zeros and then a 4 or 5. So because that's so low, it looks like that jury selection was not, in fact, random. And in fact, the Supreme Court ultimately rejected randomness. Polygraph tests, these are real results that we know are accurate because they were obtained through a controlled experiment. I think it was the Department of Defense that sponsored it, but they got people to actually tell the truth and tell lies so they knew what was what. So these are real results. And a point I would make here, well, a couple of points, that two-way tables in general are great for probability exercises, the addition rule, the multiplication rule. Great format for testing hypotheses about contingency tables. And also, they're a great medium for introducing important terms that all of our students should know. Positive result, negative result, false positive, false negative. So that lie detector table or drug results or some kind of a treatment. Those are terms that students should know. They're not formal, standard statistical terms, but it would be great if our students came out of our stat course knowing them. So false positive, false negative. And these are things that are going beyond the mere content of statistics. So one point that I'd like to make is that in this intro stat course, we have a tremendous opportunity that we really should take advantage of to go beyond the mere teaching of the content of the course. Wants to jump ahead of me again. Don't know why it's doing that. Okay. There we go. Redundancy and probability. If you teach the multiplication rule, I would definitely stress illustrating the principle of increasing the quality of systems by having redundant systems, direct result of the multiplication rule. Give examples students that are meaningful that they could learn something from, like the dire consequences of having errors on their resume, like misspellings. That's like death on a resume. Tattoos, how it might affect their employment. I'm not going to get preachy to students about tattoos or not getting tattoos, but I think it would be good for them to understand that having a lot of visible tattoos could have an effect on employment, and surveys show that, and the effects of drunk driving. Case 5, the O.J. Simpson trial. It involves confusion of the inverse, which ultimately relates to what's often called the prosecutor's fallacy. Confusion of the inverse. The example I love to illustrate confusion of the inverse is this. What's the probability it's dark outside if it's midnight? What's the probability of dark given that it's midnight? Like 1. Flip it around. What's the probability that it happens to be midnight if it's dark outside? Okay. Depending upon how you measure that, it's either 0 or very close to 0. So flipping those around can have a tremendous impact on what you conclude. And I'll talk about this in a case a little bit later on, but think about how that applies to something like, what's the probability a defendant would have a description that matches a perpetrator given that they're innocent? And that might be very low, and you could demonstrate that that might be very low. But is that the same as the probability of their being innocent given that their description matches the probability? They could be radically different. And a clever prosecutor can take advantage of that. So in the O.J. Simpson trial, they said that very few battered women are killed. The probability of being killed if you're battered is very low. The prosecution failed to show the irrelevance because the probability of Nicole Simpson being killed was 1. It was not very low. So I guess that should be the defense, right? Yeah, the defense, I think those should be backwards, but you could see what happened there. Just a confusion of the inverse, which happened right there on this slide. Case 6, this is not really a crime, but it's a case that I got involved with. A former student of mine came to me. He had been elected county clerk in my county, and oh, I know what I'm doing. I'm hitting some of these backwards too. Let's see. Oh, okay. I'm advancing it instead of retreating it. If I could get back up. Ah, there we go. So he came to me. He had been elected county clerk in Dutchess County and should have been easily reelected. But it turns out that he lost his reelection. Main reason that his father, who was a local politician, got arrested for bribery. So the same name got dragged through the press. So he lost the election. And he came to me as my former student, and he said, I want to contest the election. So look at these results. Here's the Republican line in the different townships in Dutchess County. And just look at the variation, just get a general impression of it. Here's the Democrat line. Just look at it, get a general impression of the variation. There's the conservative line, general impression. The Liberal Party line. And then this row H. Okay, and I saw that, and that got my attention, a definite outlier. I looked at that and said, whoa, that's a statistical term. So he got an attorney, and they pursued it. They went to New York State Supreme Court, where I testified as an expert witness in favor of my former student. And here again, I found that I calculated p-values, I did statistical significance, but I think ultimately it came down to this slide. Looking at that graph, that really carried a lot of impact in terms of convincing the Supreme Court judge to overturn the election. And based on my testimony, he ordered that there be a revote in this one particular town. And if that had happened, probably my former student would have been reelected. But then they took it to the appellate court, where they ruled that not on the basis of the testimony or anything like that, but they should have contested that ballot before the election, not after. And so they dismissed the turnaround. One thing that came up, though, like I used confidence intervals at one point, it was surprising to me. The attorney for my former student basically asked me one question: what did you find? And I proceeded to speak, I think, for about 45 minutes, uninterrupted. I expected the other attorney to be jumping up, I object. No, I spoke uninterrupted for about 45 minutes. And then when I finished, the other attorney said, I had used the confidence interval. And he said, well, if you take the 3% margin of error and you add that to the 5% from the 95% confidence, you get 8%, which is really high. Now, those of you that know anything about statistics know that that is totally absurd. You just can't add that 3% to that 5%. And there was statistical illiteracy in law that greatly damaged the defense. And so my point here is that even attorneys should know basic statistics. I don't know, I never had problems with this before, but for some reason today, okay. So for real data, examples and exercises should use real data, as I've said. And ideally, throughout the course, your students are going to see enough a variety of applications of real data that they're going to see applications from whatever field they might be interested in. Case 7, highlight. This was in Miami. An auditor noticed that when some unusually bets were made, certain players won games much less than others than they were expected to. So a statistician was called in to analyze the data. Now, here you have what's called an X-bar chart, typically not included in our typical intro stat course, but they're really neat tools. And basically, this is an X-bar chart for the mean. It's showing you variation of the mean. So that center line is the mean of all of the mean amounts that were bet in matinee contests. And those other lines are, loosely speaking, 3 standard deviations away. Okay, so 3 standard deviations above the mean. Oops, I'm hitting that. 3 standard deviations below it, and that's what the means should look like. And what they did here, actually, like typically you would take all of the data to develop your control chart. here they used only the data from the end, projected that backwards to look at what happened before. And you could see that something radically changed with the mean amounts that were wagered for these matinee games. And the R chart showing ranges, a measure of the variation, same kind of thing. Something changed. They became stable here, but before that, lots of variation. So one day the statistician went in and said to the prosecutors, "What happened on Valentine's Day?" And the prosecutors looked at each other, and they were dumbfounded. They said, "How did you know? We arrested the suspects on Valentine's Day." Okay? So what happened? The jury was very impressed by those control charts. They were convicted, the suspects were convicted for bribing the players. Control charts, great tools for monitoring process data. Easy to generate with technology such as Minitab. You know, when you select a technology in your intro stat course, sometimes there might be a need to go and use a different one. I could see somebody using StatCrunch throughout their course. Well, StatCrunch does have control charts, but some others that don't, like the TI-8384 calculator, and just jumping in and using Minitab for the purpose of doing control charts. This would be an excellent topic, especially if you had a 2-semester sequence. Great tools used throughout business and industry to monitor the stability of process data, to find out that your process, your production system, or whatever it is operating within statistical control. And that's a real quick 2-minute introduction to control charts. This case, case 8, Benford and Brooklyn, here I would argue that this application alone, this example alone is interesting enough to get in and do it, to do goodness of fit even if you don't. And here again, technology gives us an opportunity. You might not have time to do goodness of fit in your typical course, but you might say to your students, well, look, you've done several things. You know what hypothesis testing is about. Take this goodness of fit, Benford rule application, and here's an exercise, just go do it on your own. I'm not going to teach you, just go do it on your own. And you'd be surprised how well they can do with that. And that's a tremendous opportunity for them to take what they've learned in terms of a concept and to apply it to something that's radically different in context. So here's how it works. With Benford's law, and this works for some data sets, not all, but the leading digits have that distribution. Checks that you write tend to follow Benford's rule. Go home and check your own checkbook. Look at your checks that begin with a 1. You'll find that somewhere around 1/3 of them begin with a 1. In Brooklyn, they suspected some companies of fraud. So they got 784 checks issued by these companies, and this row right here shows the leading digits. Here's what you would expect in proportions by Benford's law. Here's what they actually found. There's chi-square, p-value, off the charts, highly significant. And here again, I think the graph, whoops, I hit the button myself. The graph does a great job of illustrating what's happening. The green line is what you expect with Benford's rule. Here are the 7 companies suspected of fraud, and you can see that it's radically different. If they agreed, they'd be pretty close together. That would be evidence showing that, you know, everything is going on normally. So something very strange was happening here, and ultimately conviction for fraud. In the same kind of test, I find they're kind of fun. You could take survey results and look at the last digit. Like if I had you all come in next class with your weights, just the last digits of your weights, I could tell whether you all actually weighed yourself or whether you reported your weights. If you reported your weights, I'd expect to see a lot of zeros and fives. So somebody that weighs 197, they would round it off and maybe put down 165. It's a nice way to detect fabricated data. Again, nice application of goodness of fit. So for randomness, you just can't make this stuff up. Randomness takes work. If you were actually weighed and you wrote down those last digits, they would tend to be randomly distributed, uniformly distributed among the 10 digits. This is kind of an aside. When I was looking over some of these things, the television show Breaking Bad, this company got the bright idea of developing this toy, Breaking Bad, where children would put together a Lego set and create their own little meth lab. Now, isn't that what you want your children to do around Christmas time? Learn how to develop their own little meth lab? You just can't make this stuff up. Case 9, footprints. Shoe prints are found at about 40% of all crime scenes. They have an extensive database with manufacturers, the models, so they could look up footprints, shoe prints. Here I have, I was able to obtain a data set of 40 results, and you could see the kind of variation that you have there. You could see that the points do fit a straight line reasonably well. The bottom is shoe print, and you want to predict the height of the perpetrator just on the shoe print. And that's a big advantage. If all you have is a shoe print on the floor and you could tell how tall the person is, that's another clue, another piece of evidence. And there I went and I got 3,981 shoe prints that the Army collected. And you could see that the scatter plots were not that different. Great class activity. Use shoe print length to predict height. So you might have everybody in your class take out a sheet of paper, trace out their shoe print, measure the length of it, and then hopefully measure the height as well. Collect the sample pair data, develop a regression equation, and you might use your own height to predict that. You might take your own shoe print, use that to predict the height, and see how it works out. Nice application of correlation regression. Great, interesting class activity. Now here again, footprints evidence. Jason Galloway and Mark Oakley, they robbed a store. They were convicted from their footprints evidence that after robbing the store, they walked back to their house in the snow and left a trail of footprints that the police just followed. You just can't make this stuff up. Okay, this one, the Collins robbery case, this might be the one that most of you are familiar with. A couple robbed, they committed a robbery, and they got several eyewitness reports, including things like the male had a mustache, the woman had a ponytail, they escaped in a yellow car, they were an interracial couple in a car. And at the trial, they presented, these are some of the probabilities that were presented at the trial. The probability of a male with a mustache, 1/4. That sounds kind of high to me. Woman with a ponytail, 1/10. Probability of yellow car, 1/10. Interracial couple, 1/1,000. And they were convicted. But the conviction was later overturned because nobody established the independence of those probabilities. Okay? When you look at these along with some others that were included there, nothing was presented that would establish that they were independent. And so for that reason, and for the reason that those probabilities were kind of just estimates on the part of the prosecution, the couple was convicted, but that evidence was thrown out and the case was overturned. This would be a nice activity again. have your students look at some of those probabilities. For example, the probability of a yellow car, that'd be pretty easy. Give them an assignment to go out, observe a bunch of cars, and find out what proportion is yellow, collect all of them in class, and develop a confidence interval, and see what you come up with, and see how it compares to what they had there. What was it, 1/10? Okay. Case 11, Brinks versus the City of New York. Parking meters. They got an anonymous tip that some of the meter collectors were stealing the money. So they went and they used videotape to record the people stealing the money. They treated some of the coins with a fluorescent coating, and they were able to go back and look at all the coins and find out that none of them had fluorescent coating. So the coins that they salted weren't showing up. 5 Brinks employees were convicted. And then later on, after that, regression was used to estimate the amount of loss. New York City wanted to go back and recover some of that loss. So they got $1 million in damages and plus $1.5 million in punitive fines. Okay? But regression was used there. I won't go into the details of that. Really, my main example here is to just illustrate that these data are available as part of the data sets that are listed in Data and Story Library. Now, on my website, which I'll show in the final slide, I've got links to different data sets. And if you go there, you could just click on them. There are a number of different sites that do this kind of thing. But I do have the Data and Story Library data set listed as one of them. So, GAZE, Greater Assessment of Innocence with a Statistics Education. Okay? But really, it stands for Guidelines for Assessment and Instruction in Statistics Education. And there are the 6 GAZE principles. And what did I do here today? This was not really a primer that would let you now become an expert to go and consult the legal community. Really, I wanted to give some different examples and illustrate some of these GAZE factors. Oh, I lost that. Let's see, I'll get it back. Okay. Have to put my glasses on to see this. Okay. On this last screen, though, I do have, and let me get right back to that from the current slide. Okay, on this last screen, I do have my email address if you'd like a copy of the slides, and I've got the website if you'd like to go and click on some of those interesting data sets. But ultimately, what I tried to do was incorporate those guidelines. Okay. I tried to use examples that illustrated the importance of interpreting results. Oh, really giving me problems today here. Ah, there it is. Okay. So interpreting results, using real data. I just can't stress that enough. That is so critically important. Use real data throughout your course extensively. Stress the conceptual understanding, the active learning, do activities, do projects. I love the idea of a capstone project at the end of the course where students apply what they've learned to some kind of an inference, maybe correlation regression, maybe a hypothesis test, maybe developing a confidence interval. They go out, they collect their own data, they work collaboratively in groups of 4, they get in front of the class and make an oral presentation, they get a computer printout, and all of these things are really incredibly important for them as individuals. Apart from just teaching the content of statistics, when we do those kinds of things, we're doing our students a real service. And we're going beyond simply being mere teachers of the content of statistics, but we're becoming better educators by allowing our students and fostering growth in those areas. Okay, so I'm just about out of time. Any questions or comments? Yes. That data set, they were mixed, but I do have the original data set with 20 males, 20 females, so it is broken down, so you could look at it that way. And I could show you where to get the data set. Yeah. Anything else? Yes. Well, you know that meth lab you saw before? No, actually, that was from a study. I read it from a study. Somebody did that, and they actually analyzed the dollar bills and used a very sensitive chemical analysis. And that's not my data. I sometimes do collect my own data, but that one was from a study. I can't think of what the source was off the top, but it was a study that was conducted. Yeah, tell them that's a very sensitive test, and the amount of cocaine that you might expose yourself to by handling dollar bills, it would be so infinitesimal, it just would not be a serious health problem at all. And if they're worried about it, tell them to just take all the dollar bills and put them in the envelope and send them to me, and I'll be happy to analyze them. Anything else? Well, thank you so much for coming.